Hello, everyone. So uh, the YouTube interface is a bit buggy, and as a result, I'm never quite sure what's coming across at your end. But I mean, my end says everything's okay. So uh, I'm just going to start right now. So what we're going to do today is just practice a couple of problems on energy. I'm going to do one problem on energy for a roller coaster type system with a spring involved, and then another one on simple harmonic motion. Okay, and the test. That'll be next week. I'll go over. We'll have a live stream on Monday and on Wednesday to prepare for it. And I haven't written the test yet, so I'll tell you on Monday what's on it. But we'll go over everything that is on the test then, and it's going to cover Newton's laws. And that short topic, kind of transitional topic on Newton's laws, but applied to planetary system and Kepler's laws, and then of course the stuff that we did on energy, and that's it. Okay, so that's it. But I don't know how many questions are on it, and yet because I haven't done it, and I usually don't think in terms of how many questions I'm going to put on a test. I usually think in terms of how long it takes me to do a test. So if it takes me 15 minutes, I expect you guys to do it in about an hour. Okay, and and I will time the test for 1 hour. All right, it'll be like last time. Okay, so let's begin. Um, the first question, like I said, is going to be one of these roller coaster type questions where something's going up and downhill. So I have a cart, and the cart weighs 150 kilograms, and it is placed. Whoops! It is placed. There we go. It is placed at rest against a large spring with a spring constant of 17 kilonewtons per meter. Okay, and the spring is compressed a distance of 1.5 meters and then released. So what you can picture is, there's a spring, and I've compressed the spring, and I've got the car. Well, it's a cart, and it's just sitting there waiting for me to like trigger the spring, and then the spring's gonna push the cart forward. Okay, so it pushes the cart forward, and then the cart's going to travel a certain distance along a hilltop, a flat hilltop. Okay, and then it's going to go downhill to ground level, and that vertical drop is going to be 15 meters. All right, so as usual, we should start with the diagram. Your diagram doesn't have to be as formal as the ones that we did for kinematics, because there you had to be very careful about your coordinate system. Here you don't have to be quite as careful. What you're really doing is you're making a diagram so that you can say to yourself, what type of energy do you have at every point in the motion. Okay, so you have kinetic energy and potential energy, and then potential energy. So there could be a couple of different types of potential energy, and the energy is going to stay constant. Okay, so I say here to start, assume no friction. When there's no friction, the energy is going to stay constant, but it's going to switch between the different types of energy. And so you want to look at the different points in the diagram and go, okay, all the energy here is all potential, the energy here is all kinetic, and stuff like that. Okay, so let's switch to my whiteboard here, and I'll draw the diagram. And I said that it starts off at a hilltop like this and then goes downhill. And on the hilltop there's a spring, so I guess here's like a wall, and attached to the wall there's a spring like this. And the spring is compressed, but it's pushing up against my car right here. Okay. And of course, then the spring is gonna release. The car is gonna move forward here. It's gonna go downhill like that. And I label 3 points. I label this point right here. Okay, I call that point number A. This is where the spring is compressed, but but the car's not moving yet. Okay, and then I label this point here point number B. Okay, so this is after the spring has sprung and it's given up all of its energy, but the car hasn't gone downhill yet, and then the car goes downhill, and this is point C. Okay, and I didn't emphasize it, but when you read the question, I tell you that ground level is down here, is H equals 0. Okay, so we're going to take H equals 0 at ground level like that. That's important. Okay, and I'm going to have to tell you I'm going to have to tell you that even on a test, because you got to calculate MGH. Okay, and you're going to get a different value of MGH depending on where you put the ground level. Like you could have put ground level up there, in which case this C would have been at a negative height. But you get you're working with different numbers, but you would get the same answers in the end. Okay, it's just the intermediate answers would be different. And to make sure, you know how I step you through problems, asking for one piece at a time. So to make sure that we're, on the same page, I do have to tell you where h equals 0 is. Okay, so this is our situation right here. And the purpose again of this diagram is to make sure that we understand what forms the energy is in. So my first question is, what's the energy at A, B, and C? The answer is some number, but it's the same at all three of those points. However, up here at the top, okay, so right there, the energy is a combination of, let's start off with the kinetic. It's probably good to go in order. The kinetic energy is 0. Why? Well, because the velocity is 0. Okay, so when I put a car up against a spring like that, and the car's not moving, the velocity is 0. If the velocity is 0, then the kinetic energy is 0. So kinetic energy is energy because something is moving. All right, and right now you just know about things moving along a line, and but later in the course, I'm going to go on to rotational motion after the test, and there things can be rotating. They're still moving, and there's a kinetic energy associated with that, known as rotational kinetic energy. But we're not considering that right now. But the point is that kinetic energy, whenever something is moving, it has kinetic energy. If something is not moving, then it has no kinetic energy. Okay. Now there's potential energy, but the potential energy can actually come from various sources. Okay. And in this case, we have potential energy due to gravity and a potential energy due to the spring. The potential energy due to gravity is mgh. Okay. And there is a potential energy due to gravity because it is on top of the hill, and the hill is, as I said, 15 meters high. Okay, so because it's at the top of a hill, it's not at ground level. Yeah, there is a potential energy due to gravity. The higher something is above ground level, the more potential energy it has due to gravity. All right, but there's yet another potential energy, and that's the potential energy because you've got a spring here. Okay, and that potential energy due to the spring, that's 1/2 k x squared, like that. Okay, and because the spring is compressed, there's a potential energy due to that. So there's no kinetic energy, but there is a potential energy due to gravity, and there is a potential energy due to the spring. All right. Um, there are other potential energies, other sources of potential energies, but we haven't studied them yet. We will. There's a potential energy due to the electrical force, which we'll study next semester. Okay, and if there were like charged particles here, then you would have yet another, contribution here. Like there would be like a third contribution to the potential energy. So there could be multiple contributions to the potential energy, but the kinetic energy, it only comes from moving things. Okay, so all right, so we've kind of identified, where the energies are going to be at point A. At point B, you might say, okay, well, what's going on here? Well, now the velocity is not going to be 0 because the car is going to be moving. It's been pushed forward by the spring, and so there is going to be a kinetic energy, and the kinetic energy is going to be given by the formula 1/2 mv squared. Okay, it's still on the top of a hill, and so it's going to have a potential energy mgh, like that. But the spring is out of the picture, and so the potential energy due to the spring, that's gone. Okay, that's going to be 0. Okay, so yes, kinetic energy, yes, potential energy due to gravity, but uh, uh, no potential energy due to the spring. Okay, and then finally, when you get down to the bottom here at point C, now you're at ground level. Okay, so you say, okay, well, it's moving, so it's got kinetic energy 1/2 mv squared. Okay, but mgh, the h is 0, it's at ground level, so there's no potential energy due to gravity. And the spring, that's long out of the picture, so there's no potential energy due to the spring. And so all of the energy at point C is all going to be kinetic energy. Okay, now whatever that number is, I think it turns out to be like 41.6 kilojoules. Whatever that number is, it's the same at A, B, and C. The total is the same. But like how it's distributed among the three here, how it's distributed among this one, that one, and that one, depends on where you are in the dynamics. And so that's really the point of this diagram. The point of this diagram is to help you to like figure out where the energy is distributed between kinetic and the various potential energies. All right, so let's switch back here. Now we're ready to jump in. All right, let me look in the chat here, and no questions. Okay, let me continue. And so now we can start answering questions. Okay, so the first question is, what is the total energy of the system at point A, B, and C? So I'm going to cut and paste my answer. I don't want to go too fast. If I'm going too fast for you, if you're taking notes or anything, then just slow me down. But I like cutting and pasting because I discovered that I tend to make too many errors when I just type it on the fly. But I'm not going to go too fast, I promise. Okay, so all right, so the question is, what is the total energy at points A, B, and C? Well, if you can calculate the energy at any one of those points, it's the same energy at every point in the dynamics. Okay, and so you could this is I guess fairly straightforward. You say to yourself, could I answer, like, could I calculate the total energy at point C? And the answer is no. We determined that at point C the energy was all kinetic, but you don't know the velocity at C. Okay, and you say, well, what about at B? Can I calculate the total energy at B? No, not really. You don't have enough. It's at A that you have enough information that you can actually calculate the total energy. Okay, but if we calculate the total energy at A, it's the same at B and at C. Okay, so here's the generic statement of kinetic energy, sorry, total energy. It's made up of kinetic plus potential. And the potential in this case is made up of two pieces. There's a potential energy due to gravity and a potential energy due to the spring. So once again, kinetic energy is because something's moving. Okay, if something's moving, it's got kinetic energy. If it's not moving, then it doesn't have kinetic energy. Potential energy is a little bit more subtle. It has to do with how things are configured. So by configured, I mean, like, if something is, like high up, like it's got some height, that's a configuration. That's like it's in a particular place in space. Okay, and so the higher up it is, the more potential energy it has, as you can imagine, because the farther something drops, the more work it can do. Okay, and the other configuration is the spring. Is it at its equilibrium? Is it compressed? Is it stretched? Okay, so that's what I mean by configuration. And potential energies are not about moving. It's just about how things are configured. Okay, and so yeah, there's a potential energy due to gravity and a potential energy due to the spring. Well, if we put the actual formulas in for those pieces, here's the potential energy, sorry, the kinetic energy, and here's the potential energy due to gravity, and there is the potential energy due to the spring. Okay, and now it's just a matter of plugging in the numbers. We have to just be careful because some of the things I gave you up there were not MKS. Okay, so the velocity is 0. Okay, because it's squished up against the spring, but it's not moving yet. So here it is. Here's the kinetic energy, and that's 0. All right, MGH. Well, let's take a look here. The mass is 150 kilograms, and there it is there. Okay. G, well, we've been kind of lazy through the course. I mean, it's technically 9.8, but we've been rounding it off to 10, so it makes our numbers easy to work with. So there it is, 10. And then H is the height, and it starts off on a hill, and I say here, goes downhill a vertical distance H. So obviously the top of the hill is 15 meters above ground level. Okay. And so H here is 15. All right. And then for the spring potential energy, 1 half kx squared, there's the half, there's the k, and if you take a look here, you'll see that I gave you k as 17 kilonewtons per meter, okay? But kilo is just 1,000, and you got to convert to newtons because newtons are the MKS units for force. And so you don't want to work in kilonewtons, but in newtons. So 17 kilonewtons, kilos 1,000, it's 17,000 newtons. Okay, so there it is, 17,000 newtons. Now you're going to see in my problems and on the test as well that I have, I'm going to have a lot of things in kilojoules. Even though joules are the MKS units, I'm going to work a lot with kilojoules, and even though newtons are the MKS units for force, you're going to see a lot of problems with kilonewtons in there. And the reason is, especially with the kilojoules, is I want you to think in terms of kilojoules. A joule is kind of a small energy of unit, and especially if you're going into a biological science, food energy can be measured in kilojoules. So here in the United States, if you buy a chocolate bar or something, and you look at the number of calories, the amount of food energy, it's in calories. Okay, but in Canada or in Europe, I've seen it even on some labels here in the US. You'll actually see the number in kilojoules, and so you can measure food energy in kilojoules. Okay, and I forget what the conversion is, but it's like a chocolate bar might be something like 100 kilojoules or something like that. Okay, so it's a meaningful number. If you worked in straight joules, then that chocolate bar would be like 100,000 joules. So kilojoules are a more meaningful number when it comes to the chemistry of food and things like that. So especially if you're going into one of the biological sciences or even in chemistry, you tend to work in kilojoules a lot. But like I said, the MKS units are joules. Okay, so that was a bit of an aside, but I want to make sure that we've all got the idea of the units right. And so our K here, the spring constant, is 17,000 newtons per meter. Okay, so the rest of it is just working out, plugging it into your calculating and working it out. This is your potential energy due to gravity. There's the potential energy due to the spring. It turns out to be 41,625 joules, or 41.625 kilojoules. Okay, now that's the energy at A, that's the energy at B, and that's the energy at C. Okay, total energy, total energy. All right, let me take a quick peek in the chat here. All right, looks okay. And so let's go on. Okay, so what is the velocity at point B? Okay, just to remind you from the diagram here, what's going on at point B, it does have a kinetic energy, okay, because it is moving, so there's going to be a term 1/2 mv squared. It isn't at ground level, it's up high, okay, it's 50 meters above ground level, so there is an mgh, okay, but there is no, where are we here? There is no potential energy due to the spring, because the spring has already, sprung. It's already given up its energy. Okay, so these are the only two terms that are going to come in there. All right, so let's switch back here, and let me cut and paste that solution. And there we go. Okay, so I started with the same formula. You can think about that formula as being valid at every point, but like I said, the spring now is sprung, so x is equal to 0. Okay, so x equals 0, it's how much is the spring compressed. Okay, so it was compressed 1.5 meters. But if it's sprung, it's sitting at equilibrium, so x is equal to 0. Okay, so when you put x equals to 0 in this term here, it disappears. Okay, and all you're left with is the mgh term for potential energy. Okay, so this reduces to that. Okay, and now what? Well, just plug in the numbers, okay? And remember what we're solving for, I asked for the velocity at point B, okay? And so if you take a look at that, you go, well, do I know all of the things in here? Yeah, you even know you know everything except for the velocity, and you even know the energy, because the total energy, because as I said, that energy is the same throughout. So even though the energy was calculated at point A, you're going to use that same number at point B, because energy is conserved. Okay, so there it is. For E, I substitute in the total energy, and that's got to equal 1/2 m. So there's the 0.5 times 150 times v squared. There's v squared. Okay, and then plus mgh for the potential energy due to gravity. Remember, we still are on top of a hill, so that's 150 times 10 times 15, and so we get this, simplifying it, and then subtracting from both sides, divided by 75, and then taking the square root, I get that number there. Okay, and on a test or on the assignments, you know that throughout the course I just said, you know what, let's work to 3 significant figures, and there it is. Okay, so at point B, this cart's going to be moving at 16 meters per second. All right, so it's moving, it's got a fair speed there. Let me just quickly see what that works out to in, just to give you an idea of what that is. That would be like close to 60 kilometers per hour. So it's going pretty fast. It's going faster than your city limit, city speed limit. Okay. All right, so there's part B, and now I ask, what is the velocity at point C? And let's go back again, just to remind you, at point C, all of the energy was kinetic, okay? It's at ground level, so there's no mgh. The spring has been long out of the picture, so there's no 1/2 kx squared. It's all mv, 1/2 mv squared. Okay, so over here, cut and paste that. Okay. So again, you could start with the same formula, but the spring is finished, so x is equal to 0. That's out of the picture. The card is at ground level, so h is equal to 0. So that one's out of the picture. The only surviving term is 1 half mv squared. So E is equal to 1 half mv squared. Okay. The energy, we know what it is because, like as I said, at every point the total energy is the same. So it's still the 41,625. That's equal to zero point 0.5 times 150 times v squared. And you solve for v, and rounding off, that's 23.6 meters per second. Okay, let me see what that turns out to be. Just I'm kind of curious how fast that is. It's going to be pretty fast. That's like 85 kilometers per hour. Okay, that's like not quite highway speed, but it's getting up there. All right, and intuitively it makes sense because at the top of the hill it was 16 meters per second. By the time it got to the bottom of the hill, it was at 23 meters per second. Okay, and so it sped up going downhill, and that's what you expect. And you should think about, you should think about your answer, see if it makes sense, because my tests are multiple choice, so there's always going to be one or two possible wrong answers that are going to be that you should be able to dismiss just based on intuition. I always do that. Okay, so if it's 60 meters per second at the top of the hill, and one of the answers is like 8 meters per second at the bottom of the hill, that's wrong. There's no way it goes downhill and it slows down as it goes downhill if there's no friction. Okay, so if there's no friction, then it's got to speed up going downhill, not slow down. All right, so up to this point, we've had no friction, and this is about all I could really ask in this question without any friction. Okay, but the next one, I'm going to introduce some friction. So let me see if you guys have any questions. Okay. All right, doesn't seem like there's any questions. Let me continue then. So now I say, assume that there is friction. Okay. And if the card is found to have only half the velocity you experienced at point C, that you expected at point C, how much energy is lost due to friction? So, like you can imagine doing this experiment. You set up, like a go-kart on the top of a hill, and you make all the measurements, and you say, oh, I expect it to be traveling at 23.6 meters per second at the bottom of the hill. And you measure it, you got your instrument there, and you measure it, and you find that it's only going like half of that. Okay, like 11.8 meters per second. You go, well, what happened? Well, what happened is that there was friction. Okay, and just to remind you what friction is, it's a force, but it's a non-conservative force. Okay, which means that it's going to convert that energy into heat. Okay, now if you don't know anything about heat, you might say, oh, the energy was lost. Okay, it's like, where is that energy? But it's not really lost. This has been converted into heat. But if you don't know about heat, then you say, well, I don't know where that energy was. And historically, for a long time, physicists didn't know about heat. It was actually Charles Joule who discovered heat, and that's why we name the energy unit after him, because even though physicists knew about the conservation of energy theoretically, every time they went into the lab to try to measure it, the energy was being lost. And they're going, we don't understand what's going on. They probably, I don't know the history that well. They probably knew it was friction, but they didn't really understand what was going on. And so, it was really Charles Joule that actually measured the heat and go, oh, that energy that disappeared from mechanical energy, it became heat energy. That's the topic of next semester. But, I want to mention that so that, we know where we're going to go next. It's kind of a bridge between the two. All right. And so this question asks, well, okay, how much energy was lost due to friction? All right, so the energy at point C, let's look at it again. That energy at point C, it's going to be less, but it's still going to be all kinetic energy. Okay, so even though it might be well, it's going to turn out to be a quarter of the energy that it was without the friction. Okay, even though it's less energy, it's still all kinetic energy. All right, and so we can calculate that by using the same formula. Let me cut and paste it here, but just substituting now half of the velocity. Okay, so let me cut and paste that solution here and go over it. Okay, so if the velocity is half of what it was in the previous question, okay, because that's what I said. So imagine, you measure your velocity and you get half of what you expected. Okay, well then the velocity is going to be 11.8 meters per second. Now I have this extra one in there with all those extra decimals, and I did that on purpose. And the reason is if you have a problems like this, and it's got one question after another question after another question, if you round off at each point, you keep introducing a little bit more error, a little bit more, a little bit more error, okay? And so that could get you into trouble. So the way I recommend, like on a test or even right now, is like in your calculator, keep all the numbers, okay? So keep all the digits, okay, in your decimal. But when you go to match the answer or report the answer like you would on a lab, then round off, okay? So I'm actually like down here when I plug in, I'm actually going to plug in all the decimals, but I mean, it rounds off to 11.8 meters per second, okay? So that's a subtle point. Students have often asked me, they say, well, I don't get exactly your answer. What's going on? Well, usually it's in one of my problems where there's several steps, and they round it off in an earlier step, and that led to a little bit more of a deviation, and then they round it off again, and it leads to more of a deviation. And if you've got enough of those going on, well, then, you're gonna be I wouldn't say significantly out. You'll still get the right answer, but you're going to deviate from it. And you're going to wonder why. Okay, so a little minor aside, but I thought I better tell you because you'll probably be in that situation during the test. Okay, so here we are at this equation here, and we don't know the energy now. Okay, it's not the same energy as before because some of that energy got converted into heat. Okay, so don't say E is equal to that 41.6 kilojoules. We don't know what it is. But we do know the velocity now and we know the mass, and so we can calculate the new energy. All right, so plugging in here, we plug in for the new velocity right here. Okay, and of course the mass is the same as before, and we get that the energy at point C now with friction is 10,406 joules or 10.4 kilojoules. Okay, and so yeah, energy was lost. And if I say, well, how much energy was lost? Well, that's your delta E. Okay, and when you do a change in energy, you do the final minus the initial. Okay, so the final is 10,406. The initial was 41,625, and you get that you lost negative 31,219 joules. The negative there indicates that it's a decrease, okay, and so the energy is being lost. All right. Again, not lost, but being converted into heat. Okay, it's like when you lose your keys. Did you lose your keys or did you misplace them? Okay, so it's not that the energy is lost; it's just that the energy is misplaced as heat, and you don't know that. Okay, all right. So great, we've got that answers that question. It was like how much energy was lost to friction. Okay, and then finally, if the cart travels a total distance of 500 meters, what is the average force of friction along that path? I'm going to show you what that 500 meters means in a second, okay? But before I do this, let me remind you that during one of the pre-recorded lectures, I talked about the work energy theorem. And, it was a pretty theoretical discussion, okay? And I didn't even prove the work energy theorem for you. I just kind of illustrated it. And you go, why did you even bother with that work energy theorem? And the reason is that the conservation of energy is not always applicable, whereas the work energy theorem always is applicable, okay? So when there's friction involved, you got to kind of fall back on the work energy theorem. And what the work energy theorem did is it really kind of related forces to energy through the concept of work. Okay, that's why it's an important idea. So work is actually, by definition, the force times the distance times the cosine of the angle between the two. So if you've got a situation like this, so this is a vector here which represents, my thumb here is a vector which represents, say, a displacement. Okay, so like a block is moving along the ground here. And my index finger here is like a force. Okay, so there might be other forces involved, okay, but this is a force. And then there's an angle in there, theta. There's a work due to that force, even though they're not in, the two aren't in parallel with one another, because again, there might be other forces. There's a certain amount of work due to that force, and it's calculated by the force, F, times the distance, times the cosine of the angle between the two. Okay, so that's the definition of work. Okay, and well, I'll give you sort of the work energy theorem in a second. Let me just say what the work is due to friction. So the work due to friction is actually very easy to calculate, because if something is displaced in one direction, the force of friction is always in the opposite direction. So it's moving this way, the force of friction is in the opposite direction. So you ask, well, what's the angle between those? And the angle is 180 degrees, and cosine of 180 degrees is negative. Okay, so the work due to friction is the cosine part, cosine theta is just negative, just a negative sign. All right, well, having explained that, let me now do this, and I guess I still have to show you the 500 meters. But let me do this first, and then I'll show you what that 500 meters is all about. So here is the work due to friction. Okay, again, the definition is FD cosine theta, but that cosine theta, cosine 180, that's this negative sign right there. Okay, and so there's the work due to friction. But that work due to friction is the energy lost. Okay, so one way to think of work is it's a transfer of energy between one type of energy to another. Whenever there's a transfer from one type to another, you can think of it as a work. Okay, and so this friction, because it's transferring energy from this mechanical energy into heat, it's doing work. Okay, that's the way we use the term. All right, but that change in energy, that is exactly that work. Okay, it's kind of like a bank account. You could think of the bank account as the energy, and transferring money out, that act of transferring money out, as work. Okay, so if you have $100 in your bank account and you transfer out 10, okay, well then your bank account is 90 because you transferred out 10. That 10 is the change. Okay, so the work is the change, and so here you have that change in energy is equal to the work. That is the work energy theorem, basically, in a nutshell. Kind of bit of a hand waving way of doing it, but intuitively that makes sense. The change in energy is that work. Okay, and it's the work due to friction in this case. Okay, so for the work due to friction, it's just the number. It's just the energy lost. Okay, and that's got to equal the force of friction multiplied the distance over which that friction acted. And you'll see that negative sign there. That negative sign there cancels with that negative sign there. So you just take the 31,219 divided by 500, and you find that the force of friction is equal to, on average, 62.4 newtons. Okay, so that's 64.2 newtons. That's an average. Okay, because you might have, friction might have been a bit higher, might have been a bit lower, so it might have fluctuated. But as you calculate that work due to friction all the way along that path, it's got to add up to that the total amount of energy lost. Okay, that's again the work energy theorem. All right, so I hope that metaphor helps. Okay, just think of like whatever the change in energy is. That's like the money taken out of your account. That's like the energy taken out, and that work is the transfer. Okay, so it's like so much energy was transferred out. All right, and there it is. And that transfer of energy, that work, is related to a force. And so the work energy theorem is what relates force to work to energy. All right. Okay, so last thing is, what's that 500 meters? Like, where is that in the diagram? Let's go back to the diagram here. And that 500 meters, it's the full path along which the force acted. So it's like the drop here is 15 meters, but it's like that full path along here, all the way along this path, no matter how curvy it is. Okay, no matter what the details. If I were to measure all the way along this path here, okay, it would turn out to be 500 meters. I mean, that's what I said in the problem. Okay, so the D in this FD, that's the full path length, irrespective of how curvy it is. Okay, and you might say, well, how would I experimentally measure that? You could I guess you could use a rope and then straighten out the rope and then compare that to a ruler, or there are lots of ways of doing that, but it's basically whatever that total distance is along the curve. All right, so this kind of covers that entire question, and it's really all based on, well, I guess the friction part is based on this, okay, but the rest of it all seem to revolve around that, okay, and you really don't know about any other kind of potential energy. The only potential energy you know, or contributions to potential energy you know, are mgh due to gravity and 1/2 kx squared. Okay, others will come later in the course. Well, actually next semester, I guess next year. So there it is. But you can get pretty creative with this. Okay. So before I move on to the next question, what I want to do is I want to show you a variation on this. There are lots of variations that I could do, but I want to show you one that you might not have expected. But it's a good variation to think about. So let me switch back to the whiteboard here, and I'm not, like I said, I'm not actually going to solve this. But what I am going to do is I'm just going to set it up, okay? And so imagine that you have like ground level here, and you have a spring like this. And the spring is upwards like this, and maybe there's a platform here like this. And then on top of the platform, you have a mass like that, okay? And the spring has been compressed some distance x, okay? And the spring has some spring constant K like that. And I guess I've also got to tell you the mass M here like that. All right. And that spring is just the mass is just sitting there. It's not moving. And I release it. And of course, what this is going to do is it's going to go uphill like that, or uphill. It's going to go up into the air, a distance h like that. And then eventually it's going to stop up here and then come back down. And I want to know, how high does it go? All right. How high in the air does it go? Okay, and you might think, geez, how do I solve that? All right, and I guess I'm just gonna say one more thing. H equals 0. Let's take h equals 0 right there, right at the bottom of the mass before it moves. Okay, well, actually, this problem is pretty easy to do. Okay, even though the dynamics in the middle here can be very complicated, the solving this problem, solving for h here, okay, is actually pretty easy, because all you have to do is use energy consideration. So you say, okay, what's the energy down here? Okay, what's the contributions to the energy down here? Well, it's not moving, and not moving, as soon as you hear not moving, the kinetic energy is 0. So that 1/2 mv squared is 0. Okay, and it's at ground level. Well, not really ground level down here, okay, but it's at h equals 0, and so mgh is also 0. So I guess h equals 0 means that your mgh is 0. And you say, oh, but the spring is compressed, and so all of the energy is in 1/2 kx squared. Okay, which you can calculate, because in principle I've given you x and I've given you k. Okay, so if I give you x and k, some numbers for x and k, you can calculate that. And I don't know why I put a cube there. That's a square. Okay, there we go. And then you go, all right, well, there's going to be all sorts of complicated dynamics in there. We'll talk about that in a second. But up here, you say, well, guess what? It's reached its maximum height. And at maximum height, the velocity is 0. So the kinetic energy is 0. Well, the spring is out of the question, so x is equal to 0. So the spring potential energy is at 1/2 kx squared. That's 0. All of the energy is, h is not 0, so all of the energy is in mgh. Okay, and so this is kind of cool, because all of the energy was 1/2 kx squared here, and then all of the energy becomes mgh there like that. And to answer the question, you just equate the two, because energy is conserved. Okay, and so this problem, if I were to ask, like any of the details, like say right here, this could be very complicated, because halfway between, or not halfway, but at some fraction of the way between the top and the bottom, you're going to have all three. The velocity is not going to be 0, because it started to move. Okay, the height is no longer 0, because it's moved up a little bit, and maybe the spring hasn't even finished uncompressing, and so at some intermediate point it could have all three energies, and so it could be very complicated. So the intervening dynamics here could be very complicated, but if all you're worried about is an initial down here and a final up here, without concern about the middle, it actually turns out to be a very easy problem to solve. Okay, so I don't know, I just wanted to show you yet another possible um, situation where you have these three energies. You have a kinetic energy, the 1/2 mv squared, then you have a potential energy due to a spring and potential energy due to gravity, and you can do a problem with that. All right, let me see if there's any questions in the chat here. All right, so no questions. Let me do our last question here. So this last question is on a harmonic oscillator. All right, so for harmonic oscillator, um, oh, that's weird. I've got it written twice here. Let me get rid of this. Okay, so for harmonic oscillator, uh, we did that when we did the kinematics, but I just described the kinematics. Now we have the dynamics of an oscillator. In other words, what drives the oscillation back and forth? And the answer is, it's that restoring force, F is equal to minus kx. Okay, and so that's the force of a spring. And so oscillators and springs are intimately related to one another. Okay, and oscillators. You might say, well, what is an oscillator? Like, can you point to some real oscillators, some concrete examples in the real world? And they're all over the place, so it's kind of hard to point them out. But like, even the little cilias in your ear, they're little fibers. They'll vibrate back and forth, which is what's happening now as you hear me. Okay, they'll vibrate back and forth. And even if you looked at them, they don't have like a spring. You wouldn't see like a little spring in there, but the fiber itself has a certain rigidity to it. Okay, and that rigidity, that's K, that's the spring constant. Okay, so even though you don't see a spring there, just the rigidity is the spring constant. So maybe a better name than spring constant would have been a rigidity constant, but everyone calls it a spring constant, so we'll call it a spring constant, even if it's not a spring there. Or another example might be like a skyscraper. You can go to something really big, and if you've ever been in a really large building and you go all the way up to the top, you might think you're crazy because you feel it maybe moving a little bit, and it is because these things oscillate, especially when they're windy, and that oscillation you'll feel it, and again, because even though it's a large structure, it does have some rigidity to it. The rigidity is not infinite. If it were infinite rigidity, like K equals infinity, it's not going to oscillate at all. It has some finite rigidity, and so they oscillate as well. Okay, so having said that, let's do this problem, right? So an oscillator has a mass of 150 grams. We're going to have to convert that to kilograms. And it's found to have a period of 0.37 seconds. And that's the time it takes for the oscillator to make one complete cycle. Okay, so it takes 0.37 seconds. That's what you would measure in the lab. And then I tell you that when it is 2.5 centimeters from equilibrium. So remember that an oscillator oscillates symmetrically around equilibrium. So when it is 2.5 centimeters, a distance of 2.5 centimeters from equilibrium, it's still moving. And it's moving with a velocity of 0.5 meters per second. Now, it might be moving out or might be moving in. It doesn't matter. When it passes that 2.5 centimeter mark, either on the way in or on the way out, it's going to be traveling at 0.5 meters per second. And the reason is that it's symmetrical that way. Remember, like with projectile motion, when we threw something up and it came down, when it passed the same height, the velocity going up was the same as the velocity going down when it passes the same height. It's the same thing with an oscillator. So when it passes that 2.5 meter mark, no matter which way it's going to be traveling at 0.5 meters per second. Okay. So I give you that information, then I ask some questions. So the first question is the angular frequency. Whether I ask for this question or not, you're probably going to want to calculate this right away because the angular frequency comes up in all the equations, okay? And that's that symbol omega, all right? So its relationship to the period, very simple. It's just 2 pi, omega is equal to 2 pi over t, over capital T. So there it is, okay? So omega angular frequency is equal to 2 pi divided by capital T. Substitute in for 2 pi, T I gave you, and it turns out to be 17.0 hertz or 17.0 per second. Okay, so hertz is per second. We saw that when we did the kinematics. All right, well, that was trivial, but I put it there because we're doing this together. But if I went straight to the spring constant, without asking for the angular frequency, you would still have to calculate that angular frequency, because in order to get that spring constant, you need the angular frequency. Why? There's a relationship between mass, spring constant, and angular frequency. Okay, so those three go together. And that we discovered out of the dynamics. Okay, and since you're the calc class, I actually proved that for you by doing some differentiation. Okay, so there's a relationship between K, M, and omega. And what is that relationship? Yeah, here it is. All right, right there. Okay, so omega is equal to the square root of K over M. All right, well, we want to solve for K. And so let me isolate that. So square both sides, I get omega squared is K over M. Multiply both sides by M, and I get that K is equal to M omega squared. Substitute in. M is, I told you it was 150 grams, but we got to convert that to kilograms, so divide by 1,000. It's 0.15 kilograms. Multiplied by omega, we found omega to be 17, so 17 squared, and that tells us that the spring constant is 43.35 newtons per meter. Okay, so easy enough, but as you can see, omega was critical in calculating that. Okay, what's next? So next I say, what's the total energy of the system? So the energy of the system, you can calculate it in, I gave you like 3 formulas for it. One of them was if you knew the amplitude, you could calculate it, because when you're at the end point, there's no velocity. If there's no velocity, there's no kinetic energy. It's all potential energy. And you can calculate the energy, the total energy, by just using 1 half Ka squared. Instead of x, you use a because x is equal to a out there, and there's no velocity. The other one was if you know the velocity right at the middle, because there's no potential energy. X is equal to 0, so there's no potential energy, all kinetic in the middle, and you use 1 half mv max squared, okay? And the way it goes is it's all potential energy out there at the end point. It's all kinetic energy at equilibrium, all potential energy at this endpoint, all kinetic energy, all potential energy. And what if you're somewhere in between? Well, then it's a little bit kinetic and it's a little bit potential. And that's the situation you're in right now, because I told you that at 2.5, a displacement of 2.5, you have an energy of 0.5, a velocity of 0.5 meters per second. So I didn't tell you the amplitude. I didn't tell you the maximum velocity. I gave you information at some arbitrary point in the cycle, okay? And so here's that answer. All right. Okay, so the energy is the sum of kinetic and potential. Okay, there's no gravitational potential energy here, and the oscillator does have an implicit spring attached to it, and so the potential energy is spring potential energy. Okay, so here's the kinetic energy, 1 half mv squared. Here's the spring potential energy, 1 half kx squared. Okay, and then we just substitute in the numbers. Okay, and that's easy enough. Mass was 0.15. The velocity at that particular point is 0.5 meters per second. Okay, and then k we found to be 43.35, and x here, that's at 2.5 centimeters, 2.5 centimeters, but we got to convert to meters, right? And so 2.5 centimeters is 0.025 meters. Okay, and then working that out, here's the kinetic and here's the potential. That works out to a very small energy, actually 0.0323 joules. Okay, so small energy, but not zero. All right, so there we go. We have the total energy. Now, here's the point about total energy. If you can calculate the total energy at any point, it's the total same as the energy at every point. Okay, let me say that again. So if you calculate the energy at any point, it's the same energy at every point. Okay, and so I gave you the information to calculate the energy at some arbitrary point here, but that's going to be the energy at the end point, and it's going to be the energy at equilibrium. Okay, and so the next question is, what's the amplitude? Well, when you're out here, when x is equal to a, well, then you can just put an a here for x, like that. But what's v at the end point? It's 0. Okay, so this term totally drops out when you're at x is equal to a, and this formula reduces to this. Okay, when you're at x is equal to a, in other words, you're at an endpoint. Okay, the velocity is 0, so the kinetic energy drops out, and your 1 half kx squared is 1 half ka squared. Okay, and since you calculated the energy at one point, and it's the same energy at every point, it's the same energy here, and so we know E. We know E, we know K, and we can find A. All right. Now, what I did here was, rather than plug in the numbers right away, I just rearranged. I like doing that personally. I mean, you could do it whatever way you like, as long as it's correct. Okay. But I just rearranged it here. So what I did was I took this equation. I multiplied both sides by 2 and then divide both sides by k, and that isolates a squared. And then I take the square root of both sides, and I find that the amplitude is equal to the square root of 2e divided by k. Okay, well, then just plug in the numbers and work it out, and it works out to be this number here, 0.0386. That's going to be in meters in MKS, and since we've been working in centimeters, I converted it to centimeters, so it's 3.86 centimeters. Okay. Ask yourself, does that make sense? Well, let's think about it. When you got into 2.5 centimeter point, you were still moving, and you were moving outwards. You could be moving inwards, but you could have been moving outwards. So if you're at 2.5 centimeters and you're still moving, then you're going to move past 2.5 centimeters. Okay, so I can't tell you from just that sort of reasoning how far past 2.5 centimeters you're going to go, but you're definitely going to go past 2.5 centimeters. And sure enough, your answer turned out to be bigger than 2.5 centimeters. Okay, now on the test, I'm always going to give you some absurd answer. So one of the answers might have been like 1 centimeter. Well, you can immediately dismiss that because you know it has to go past the 2.5 centimeter mark. Okay, so just keep that in mind. It also, it helps you to not make a mistake. If you got an answer of like 1 centimeter at this point, you should go, wait, that makes no sense because we know that it's going to make it to at least 2.5 centimeters, and in fact, it's going to go further because it's still moving at 2.5 centimeters. So yeah, it's got to be bigger than 2.5 centimeters. Okay, now the next one is kind of like the inverse of this one. Here we're in the middle. And in the middle, x is equal to 0, and the energy is all kinetic, okay? And so here's the solution to that one. All right, like that. All right. So you say, well, what happened to the 1/2 kx squared? Well, x is equal to 0. It's gone. And v is v max at equilibrium. And so that's why I just, just to be correct here, I just replaced v with v max. Okay. Well, same thing. I just rearranged. And you can see here, it looks almost the same as the previous one, and only instead of a k here, you have an m. And so V max is equal to the square root of 2e divided by m, and that turns out to be this number right here, okay? 0.7174, okay? And you ask yourself, well, does that make sense? Well, when you're out here at the end point, your velocity is 0. You're coming in, coming in, coming in. You pass the 2.5 centimeter mark. You're traveling at 0.5 meter per second, but you still have more to go. And so as you move from that 2.5 centimeter mark in, you're going to speed up, speed up, speed up, speed up, speed up. So again, I can't tell you how fast it's going to go, but I know that it has to be faster than 0.5 meters per second because you were out here and traveling at 0.5 meters per second. So by the time you get to equilibrium, you're going to be going faster. And in fact, the number turns out to be 0.7, which is bigger than 0.5. Okay? And then the final question is, I said, well, I calculated the energy at one arbitrary point. Let's use that to find the position of another arbitrary point. That's the point at which it has a velocity of 0.6 meters per second. Okay, and there, you use again the formula for the energy. And I'm asking how far from equilibrium. As soon as you hear how far from equilibrium, that's x. So I'm asking for you to calculate x like that. You're at an arbitrary point, so you can't use this equation and you can't use that equation. You got to use the generic one. There it is, like that. Okay. And I tell you some of the numbers. Well, first of all, you know the energy, right? Because calculated at one point, it's the same energy everywhere. There it is. Okay, and then 1/2 mv squared is same as above, but now the velocity I tell you is 0.6 meters per second. So 0.6 meters per second. There it is. Okay, and we have all of these things. We don't have x, but that's what we're asked to calculate. Okay, so substituting in all the numbers, we get that. All right, and then simplifying it and solving for x, I find that x is equal to 1.564 centimeters. Okay, so once again, I had to use the general equation there because it's not at the end point and it's not at equilibrium. It's at some arbitrary point. Okay, and I gave you the information that the velocity was 0.6 meters per second. There it is there. Okay, you know the total energy because you calculated it already, and you can solve for x. All right. Again, ask yourself, does this make sense? And it does, because let's see here. So you were at the 2.5 centimeter point and you were traveling at 0.5. If you're going to speed up to 0.6, then you have to be heading inwards, because if you go out from the 2.5, you're going to slow down. If you're at the 2.5 and you go in, you're going to speed up. So you're going to speed up from 0.5 to 0.6, and that's going to happen at the 1.564 centimeter mark, okay, which is closer to equilibrium, and that makes sense. Another way to think about it is that from 2.5 centimeter mark, where your velocity is a half, to equilibrium, where it's 0.7, somewhere in between there, somewhere between 2.5 and 0, that's where you're going to hit the 0.6. It turns out to be at 0.1564 centimeters. Okay, so just thinking about it this way, it helps you to, at least eliminate incorrect answers and make sure that you didn't make any mistakes. Okay, well, that's it for the class today. Let me see here if there's any questions in the chat. So no one asked any questions. I assume you understood everything that I did. But let me just say here, does anyone have any questions? Oh, I can't type. If not, we're done. All right. All right, doesn't seem like anyone has any questions, so this was pretty clear. I guess that's a good sign. It either means no one wants to ask questions, or it was all very clear. So I'm gonna let's say goodbye. So I should explain why I wave at the end. This is because there's a lag, and at least then I know that I can see myself waving. I know that I've said goodbye. I know it's kind of cringy, but that's the only way that I can tell that I'm actually done with the stream. Okay, bye bye, guys.